This paper reports on the development of a geocomputational simulation workflow designed for the irradiance mapping of large-scale city models. A fully automated workflow is presented. The workflow imports city models in the CityGML format, generates the simulation input models, executes the simulations, and aggregates the results. Simulating irradiance. Various tools exist for performing irradiance simulations of 3D models. However, these tools are typically used with relatively small models. For example, the 3D model may include 10 or 20 buildings. In order to support city planning, simulations of large-scale city models are often required. When running such large-scale simulations, various issues arise related to the scalability of the processes and tools. The aim of this research is to provide an automated irradiance mapping workflow for the simulation of large-scale city models. The workflow calculates irradiance on all building surfaces, irrespective of whether the surface is opaque or glazed. This presentation will describe the workflow and show two case studies, one of Singapore and another of Rotterdam. The case study models have hundreds of thousands of buildings and millions of polygons. Three key components in the workflow are the CityGML modeling standard for 3D city models, the radiance simulation engine for calculating irradiance, and SideFX Houdini software for scaling and automating the workflow. Each of these three components will first be briefly introduced. CityGML is a standardized format for 3D city models. For the proposed workflow, models saved in the CityGML file format are used. Though city models in other file formats could be used as well, the CityGML file format is preferred, as it is an open, standardized, XML-based format. The CityGML format includes semantic information and allows models to be described at varying levels of detail, referred to as LOD. In this research, LOD2 models were mainly used. Radiance is a suite of validated programs widely used for lighting simulation. Within this research, two specific programs were used, called GenCumulative Sky and RTrace. The GenCumulative Sky program generates a model of the sky. The sky model describes the cumulative irradiance distribution for a specified time period across the sky hemisphere. The RTrace program computes radiance values at specific points within a model. The RTrace program is designed for relatively small model. Hence, we identified the need to design a workflow that is able to handle an input model consisting of millions of polygons. Houdini is a procedural 3D modeling application developed by SideFX. Houdini has been designed from the ground up with performance and scalability in mind. In March 2019, SideFX released Houdini 17.5, which included a new feature, Procedural Dependency Graph, PDG. PDG was developed to better scale and automate processes by distributing tasks across multiple CPUs. In the irradiance mapping workflow, Houdini is used to process geometries and to execute irradiance simulations, relying on PDG for its multi-threading capability. In order to support this workflow, we have developed two plugins. A plugin for importing CityGML models. The plugin imports both the geometry data and the semantic attributes from the CityGML model. And a plugin for executing RTrace simulations. The plugin includes a graphical user interface for configuring various simulation settings. Next, let's look at the irradiance mapping workflow. The proposed workflow consists of 7 steps as shown in this figure. A key strategy of the proposed workflow is the decomposition of the city model into smaller building models for parallel simulation. The Houdini PDG was used to automate the process of splitting up the model and running RTrace simulations in parallel. Let's go into the details for each step of the workflow. In step 1, the model encoded in the CityGML files were imported into Houdini and saved in the native BGO format. Polygons that are below 10 squared meters are considered too small, and are tagged. Other invalid geometries are also fixed while importing. In step 2, the centroid of each building is calculated. The building centroids are translated up in the vertical direction to the maximum height of the building. Centroid points therefore capture both the location and height of the building. All building centroid points are then saved in a single file, which is used later, in Step 4, when generating the input models for the simulations. For each building that is simulated, a surrounding context needs to be generated. The centroid points are used for deciding whether a building should be considered as part of this context. This will be explained in more detail in Step 4. In Step 3, a low-resolution model is generated for each building, by shrink-wrapping the building, as shown in the figure. This shrink-wrapped buildings are used later, in order to speed up the simulation. In Step 4, the context geometry for each target building is generated. Neighboring buildings within a given radius of the target building are added to the context geometry. This is so that the impact of shading from neighboring buildings can be accurately captured. Two bands of neighboring buildings are defined. The inner band consists of neighbors within 400 meters of the target building. For these buildings, the full resolution models are used. We refer to these as the near neighbors. The outer band consists of neighbors between 400 to 800 meters from the target building, and that are taller than a certain height threshold. For these buildings, the low-resolution shrink-wrapped models are used. We refer to these as the far neighbors. For finding neighbors, the building centroids calculated in Step 2 are used. Buildings that are too far would have minimal influence in the irradiance values, and are therefore excluded. For the far neighbors, the height threshold is based on a 5-degree angle, as shown in the diagram. The two red lines demarcate the 5-degree lines extending from the 400-meter mark. Buildings with heights that protrude above the 5-degree line will be included in the context. Note that the 5-degree and angle the 400 and 800-meter thresholds could be changed, depending on the urban form of the city and the lowest sun angle. In Step 5, for each building in the city model, an IRRADIANCE simulation is executed. Note that if there are hundreds of thousands of buildings in the city model, then this step will be repeated hundreds of thousands of times. This step includes a number of sub-steps. First, each target building together with the near and far neighbors are loaded into Houdini. Each surface on the target model is then subdivided into patches of 3 by 3 meters. The surface subdivision ensures that irradiance is sampled evenly across all surfaces. We refer to these smaller surfaces as surface patches. Then, an input file is generated for the analysis points, in a format required by the IRRADIANCE simulation. The file contains the centroid and surface normal of each surface patch. Finally, the IRRADIANCE simulation is executed. The inputs including the analysis points, the neighboring buildings models, and the cumulative sky model. Finally, in Step 6 and 7, the simulation results are aggregated and processed. The data for each building is saved in two formats: as a BGO file and as a CSV file, containing irradiance data along with various other attributes. The resulting data is then aggregated into a number of master files, based on the city districts. The first case study focused on Singapore. For the Singapore case study, a city GML LOD2 model of the whole city was simulated. The city GML model contained 156,000 building structures. After filtering out small buildings and other small structures, 132,000 buildings were further analyzed. The final simulation for the Singapore model took 160 hours to complete on 36 cores, each 2.6 GHz. The results of the simulation were further analyzed and studied using the Tableau data visualization tool. The window-to-wall ratios for roofs and facades for different building types were determined through other surveys. These were then used to calculate the solar PV potential achievable in each district. The second case study focused on Rotterdam. For the second case study, a city GML model of Rotterdam was simulated. In this case, the model contained 3 different LODs. For the simulation, the LOD2 and LOD1 models were extracted. The workflow was modified so that, instead of shrink-wrapping, the LOD1 models were used for the low-resolution far neighbors. In total, the model included 200,000 buildings, divided into separate districts. This image shows just one district, with 6,500 buildings. A closer look at the simulated model reveals the level of detail in the simulation results. The context radius settings used in Singapore model was found to be insufficient in the context of Rotterdam, primarily due to the low sun angle. Hence, the context radius settings were increased for Rotterdam model. Due to the larger context radius and greater number of buildings, the Rotterdam simulation took longer to complete. The final simulation took 230 hours to complete, again using 36 cores, each 2.6 GHz. The table shows a breakdown of the time spent on each step. Conclusions. A scalable irradiance mapping workflow has been developed that can be used for simulating large-scale city models. Use of the validated radiance simulation engine ensures that reliable results can be achieved. The results of these simulations support decision-making on deployment of solar PV in cities. Future research will investigate the use of city GML LOD3 models in which windows are explicitly represented. This will allow more accurate predictions to be made with regards to solar PV potential. In addition, we are also investigating how similar workflows could be used for other types of simulations. We would like to acknowledge the support from Singapore Land Authority for providing access to the City GML database of Singapore. We also thank Solar Energy Research Institute of Singapore for leading the solar potential studies for Singapore. Thank you very much for your attention. Please visit us at designautomation.net. This video is produced using CodeSteamer.